Evaluating the suitability of a 1500 kV transformer for a 3000 amp panel operating at 480/277 volts, 3-phase, 4-wire requires careful consideration of several factors. The provided information includes a total connected kilovolt-amperes of 2581, a total connected amperage of 3105 amps, and a feeder amperage of 2912 amps. Firstly, the transformer's kilovolt-ampere rating must be adequate to supply the connected load. While the 2581 kilovolt-amperes connected load is less than the 1500 kilovolt-ampere transformer's rating, this comparison alone is insufficient to determine suitability. Secondly, the transformer's amperage capacity must be evaluated. A 1500 kilovolt-ampere transformer at 480 volts, 3-phase has a full load amperage rating calculated as follows: kilovolt-amperes divided by volts, divided by the square root of 3. That is, 1,500,000 divided by 480 divided by 1.732, which equals approximately 1804 amps. This calculated amperage is significantly less than the total connected amperage of 3105 amps and the feeder amperage of 2912 amps. Thirdly, the power factor of the load is a critical factor. The calculations above assume a power factor of 1.0. If the power factor is less than 1.0, the actual current drawn from the transformer will be higher. The formula relating kilovolt-amperes, kilowatts, and power factor is kilowatts equals kilovolt-amperes multiplied by power factor. A lower power factor means a higher current for the same amount of real power, measured in kilowatts. To determine the minimum acceptable power factor, the transformer's kilovolt-ampere rating can be used in conjunction with the connected amperage. The apparent power, in kilovolt-amperes, is related to the voltage and current by the formula kilovolt-amperes equals volts times amps, divided by 1000, divided by the square root of 3 for 3-phase systems. Rearranging this formula, the minimum acceptable power factor can be estimated. If the connected amperage significantly exceeds the transformer's calculated amperage capacity, a higher power factor will be required. If the power factor is sufficiently low, the 1500 kilovolt-ampere transformer may be inadequate, even though the connected kilovolt-amperes is less than the transformer's rating. Fourthly, the conductor sizing and conduit fill must be evaluated according to the National Electrical Code (NEC). The information indicates the use of 7 sets of 750 kc mil-THWN conductors in 4-inch conduit from the transformer. The ampacity of 750 kc mil-THWN conductors depends on the temperature rating and installation conditions. Assuming a 75 degrees Celsius rating, the ampacity of 750 kc mil-THWN is typically around 620 to 650 amps per conductor, as noted in the question and answer. The NEC provides tables for conductor ampacity, such as Table 310.16. The total ampacity of 7 sets of these conductors is 7 multiplied by the individual ampacity, which equals 4340 to 4550 amps. This total ampacity appears sufficient to handle the 3105 amps connected load. However, conduit fill calculations must also be considered. The NEC specifies the maximum allowable percentage of conduit fill. Using multiple conductors in a single conduit can reduce the ampacity of each conductor due to heat buildup. Adjustment factors for the number of conductors in a raceway are found in NEC Table 310.15b3. These adjustment factors must be applied to the base ampacity of the conductors. Additionally, the physical fill of the conduit must comply with NEC Chapter 9. The dimensions of the conductors and conduit must be used to calculate the percentage fill. If the conduit is overfilled, it can be difficult to pull the conductors, and heat dissipation can be impaired. Fifthly, consider the overcurrent protection for the transformer and the panel. The overcurrent protection must comply with NEC Article 450 for transformers and Article 408 for panel boards. The primary and secondary overcurrent protection for the transformer must be sized appropriately to protect the transformer from overload and short circuits. The panel board must also have adequate overcurrent protection for each circuit. The available fault current at the transformer secondary must be calculated to ensure that the overcurrent protection devices have a sufficient interrupting rating. Sixthly, voltage drop calculations are important to ensure that the voltage at the panel remains within acceptable limits under load conditions. The NEC recommends limiting voltage drop to 3% for feeders and 5% overall for feeders and branch circuits. Voltage drop calculations depend on the conductor length, conductor size, conductor material, and the load current. Excessive voltage drop can cause equipment to malfunction. Seventhly, the customer-owned primary service adds another layer of complexity. The utility company typically specifies the requirements for the primary service, including the transformer size, overcurrent protection, and grounding. Coordination with the utility company is essential to ensure that the installation complies with their requirements. Eighthly, harmonic current should be considered, especially if the load includes nonlinear loads such as electronic devices or variable frequency drives. Harmonic currents can cause overheating of transformers and conductors and can interfere with other equipment. If harmonic currents are present, a K-rated transformer may be necessary. K-rated transformers are designed to withstand the heating effects of harmonic currents. Ninthly, the ambient temperature and altitude affect the ampacity of conductors and the performance of transformers. The NEC provides correction factors for ampacity based on ambient temperature. Transformers may need to be derated if they are installed in high ambient temperatures or at high altitudes. Tenthly, future load growth should be considered. It is often prudent to oversize the transformer and conductors to accommodate future load increases. A safety factor of 25% or more may be appropriate. In summary, determining the suitability of a 1500 kilovolt-ampere transformer for this application requires a comprehensive analysis that includes the low power factor, conductor ampacity, conduit fill, overcurrent protection, voltage drop, harmonic currents, ambient temperature, altitude, and future load growth. The connected amperage exceeding the transformer's calculated amperage capacity is a significant concern that must be addressed. Without more information, it is impossible to definitively determine whether the proposed transformer and conductors are adequate. A detailed load study and coordination with the utility company are recommended.